Hi everyone and welcome to the next lecture in the NPTEL course Machine Learning for Core Engineering Disciplines. In the last several lectures we have looked at the tools of unsupervised learning wherein we looked at both clustering and dimensionality reduction techniques. Now before we close our discussion of unsupervised learning, I know that we do need to have some analytical examples to give you insight into what really happens, and also a tutorial where you will work through some Python, right, and get these kind of algorithms implemented. So these will be the subject of the next few lectures, and today I will start out with some analytical examples that will tell you about clustering and principal component analysis. Of course anything that we can do analytically is subject to very small data set sizes, so that of course will be true, but hopefully that should give you enough insight as to what really happens on a computer wherein you are able to work with very large data sets. So let us go ahead and get started. So today I will cover some analytical examples or analytically solvable examples of unsupervised learning on toy data sets. Okay, so that is what we are going to do today. And the first example I want to take is that of clustering. Okay. And although typically k-means clustering is done with the Euclidean distance, just to introduce to you the concept of a city block distance which we had discussed, I want to take up the k-means clustering with city block distance. This is a bit unconventional, but nevertheless does seek to illustrate what can happen in some of these algorithms. So this is clustering using city block distance metric. Okay, and roughly we will follow the k-means clustering logic. Okay. So let us take this data set where you have 5 data points, right, and these are this is the data. So there are 5 data points each having an xi and a yi. So I am going to write this in a table here. So point 1 xi yi is 2 comma 10, for i2 it is 2 comma 5, for i3 it is 8 comma 4, then i4 it is 4 comma 8, and finally for i5 it is 2 comma 6. Okay. And like I said, we are going to consider the city block distance. So here the distance between 2 points pi and pj is defined as the sum of the distance in the x direction plus the distance in the y direction independently. Okay. And we had explained that this city block distance is basically also known as the Manhattan distance, right, or taxi cab distance that happens when you are forced to move on a grid, which really happens in large cities. As you know, Manhattan is referring to New York City in the United States. So if you are forced to move on a grid, then between any 2 points your distance will be represented by this particular equation here. Alright, so if that is the equation for the city block distance, right, and that is how we want to do clustering. So here we want to group these into 2 clusters, right. So k is 2 here, so we are doing slightly unconventional clustering using the city block distance. So this is the equation for city block or taxi cab or Manhattan distance. Okay. And you all may remember from our discussion that we do need to specify the initial clusters, right. How are the initial clusters decided? So, it has been given to you that initially consider P1 and P2 as the centers of the two clusters. Okay. So, initially this is the first point P1 2 comma 10, and then the second point is 2 comma 5. So, these have to be considered as the centers of the two clusters. Alright. So, now we will discuss how this clustering algorithm proceeds, right. So, the first step is to compute the distance of every point to the center clusters, to the center of the cluster. So, let us go ahead and do that. Okay. So, here let us see what happens. So, your I am going to compute the distance of every point I from the cluster center. Okay. And like I said, we are considering two choices, right, of the cluster centers. So, for the first cluster we are considering the first point. So, that is P1 2 comma 10, and for the center of the second cluster C2 we are considering P2, okay, and that is 2 comma 5. Alright. So, these are the two cluster centers, and we have to compute the distance of every point from these cluster centers to decide which cluster that point should be allotted to. So, the first point is 2 comma 10, the second point is 2 comma 5, the third point is 8 comma 4, the fourth point is 4 comma 8, and the fifth point is 2 comma 6, right. So, these are the 5 points whose distances we have to compute from the cluster centers. So, obviously the distance of 2 comma 10 from 2 comma 10 is 0. Now, the distance of 2 comma 5 with 2 comma 10, there is no separation in the x coordinate, both x coordinates are 2. So, in the taxi cab distance the only separation will come in the y direction. So, that is absolute value of 10 minus 5. So, that is just 5. Okay. Now, for the third point we have 8 comma 4 and the center is 2 comma 10. So, 8 minus 2 is 6, and then 10 minus 4 is also 6. So, that is 6 plus 6 equals 12, right. So, I hope you can understand how we are applying this formula here for the taxi cab or city block distance. Okay. So, just the separation along the x coordinate plus the separation along the y coordinate. Of course, if you had many more components, right, here we are considering 2 components, right, or 2 features. If you had many more features you would have to compute the distance along each of those features and then add them up. Alright. So, that is the distance of 8 comma 4 with C1. Now, 4 comma 8 with C1 is 4 minus 2 is 2, and 10 minus 8 is also 2. So, 2 plus 2 is 4. And similarly for 2 comma 6 you can compute 2 minus 2 is 0 and 10 minus 6 is 4. So, the total distance in the taxi cab metric is 4. I encourage you to fill up the table considering C2 as the cluster center, and you will then be able to see that these are 5, 0, 7 and 5 and 1, right. So, these are the distances you will get. You should work them out together. Okay. So, now which points, now we have to do the reassignment of the points. So, the question to ask is which points will now be assigned to which clusters, right. So, if you consider the first point, right, 2 comma 10, that is closer now obviously to C1, right. So, you will just assign it to the cluster 1. The second one, right, 2 comma 5. So in this case 2 comma 5 is closer to C2, so it will get assigned to cluster 2. 8 comma 4, that is closer to cluster 2 again. 4 comma 8 is closer to cluster 1, and 2 comma 6 is closer to cluster 2. So these are the new assignments that have been made, right, or basically the assignments that have been made based on the initial choice of the cluster centers, which was P1 and P2. Okay, so I hope this makes sense what we have done so far, right. So now we have to assume the new centers, right. So the new center, right, is basically C1 consists of 0.1 and 0.4. So we have to take the centroid based on these. So 0.1 is basically 2 comma 10, and then 0.4 is 4 comma 8. Okay, so this is where it gets a bit unconventional, right, because usually we define the centroid and then work with the Euclidean distance, but here we are going to define the centroid but still work with the city block distance. So this becomes half of 6 comma 18, so that is essentially 3 comma 9. So that is the new center, right, of the clusters. Earlier we had assumed the cluster centers to be just P1 and P2. Now the center of the C1 cluster is actually 3 comma 9, which is obviously different from 2 comma 10. Alright, so that is the center of cluster 1, and see here that we have divided by 2 because there are 2 points in cluster 1, only points 1 and 4. Now if you come to cluster 2, then there are 3 points here, 0.2, 0.3 and 0.5. So the centroid is going to be defined based on that. So for cluster 2 we have P2, P3 and P5. So your centroid is going to be given by 1/3 of those points. So that is 2 comma 5 plus 8 comma 4 plus 2 comma 6. Alright, so this becomes 1/3 of, you have to add them element wise. So 2 plus 8 is 10, 10 plus 2 is 12, and then similarly if you add the other 3 numbers 5, 4 and 6, you are going to get 15. Right. So now 12 divided by 3 is 4, and then 15 divided by 3 is 5. So this is the center of the second cluster, right, which is also different from what we had assumed, right, as the center to start out with. So that is the end of this iteration. So now we have to go on to the next iteration and then compute the distance of every point from these new centers, right. So again we have to make a table, right. So we have to compute the distance of each point Pi, right, from the center for both cluster 1 and cluster 2, right, and we had done this earlier. Now only change is that the center of the first cluster is 3 comma 9 and the center of the second cluster is 4 comma 5. Okay, and we have to do this again for all the 5 data points. So and those data points I'll write them down again. That's 2 comma 10, then 2 comma 5, then 8 comma 4 and 4 comma 8, and then the last row we will have to put it onto the next page here. So that will be the last point, which is 2 comma 6. Alright. So now what is the distance of 2 comma 10 with 3 comma 9? The distance is 1 along the x direction and 1 along the y direction. So that is just 2, right. Then what is the distance of 2 comma 5 with 3 comma 9? So that is 1 along the x direction and 4 along the y direction, so that is 5 in taxi cab geometry. 8 comma 4, the distance is 5 in the x direction and 5 in the y direction, so the total of 10. And then I encourage you to do the remaining calculations yourself. However, I will help you fill the table here so that you can check your calculations. Alright, so this will be 2, that is a 5 and then a 3 and then again a 3. Now once you have these new distances, you have to again reassign the points to the clusters, right. So now point 1 is closer to cluster 1, point 2 is closer to cluster 2, point 3 is closer to cluster 2, point 4 is closer to cluster 1 and point 5 is closer to cluster 2, right. So this is the new assignment. So cluster 1, right, at the end of the second iteration is P1 and P4, and cluster 2 at the end of the second iteration is P2, P3 and P5, right. So that is the assignment you can see here, right. So point 1 is assigned to cluster 1 and point 4 is assigned to cluster 2, that is what I have shown here. And then marking with a slightly different color, point 2, 3 and 5, they are assigned to cluster 2, and that is exactly what is written here, right. So this is the assignment of the points at the end of the second iteration, right. To know whether the algorithm has to be terminated, you have to compare the assignment of points with the previous iteration, that is very important. And to do that, you do need to know the assignment of points at the end of the previous iteration, and that is something actually we did not do. So let us write it down formally. So again, following a similar strategy, the cluster 1 at the end of the first iteration, it consists of this point and this point, so that is P1 and P4. And then if you look at cluster 2, right, at the end of the first iteration, that was P2, P3 and P5, okay. So this is the assignment of points at the end of the first iteration, and look, that is exactly the same as the assignment of points at the end of the second iteration, right. So that means our algorithm can now be terminated, right. So since the assignment of points to clusters does not change after the second iteration, right, we stop the clustering algorithm here. Okay, so that hopefully gives you an idea of how these clustering algorithms are working, right. So if you want, we could also sketch out these points, right. So let us try to do that. So this is the let us go to the next page. So we have plenty of space there, and we will be able to get some insight from here, okay. So if you sketch these points, so this is the y axis here and this is the x axis, right. So in x, the first point is 2 comma 10, so let us just roughly sketch it. So 2 is here, so I am denoting this as the first coordinate, and then this is the second coordinate. So 2 comma 10 is roughly here, so that is P1. Then with a different color, the second point is 2 comma 5, so that is somewhere here. The third point is 8 comma 4, right. So 8 is somewhere here and then 4 will be somewhere here. So note that this is a rough sketch, right, but still, I mean, it will give some feel for what is going on. The fourth point is 4 comma 8, so 4 is somewhere here and then 8 is somewhere here. So this is and let me do it with a different color. So this is P4, 4 comma 8, and 0.5 is 2 comma 6, okay. So using yet another color is it will be marked at 2 comma 6. So 2 is here and then 6 will be here. Okay. So these are the 5 points that we have, and you know that cluster 1 is P1 and P4. So this is essentially cluster 1, and cluster 2 is P2, P3 and P5. Okay. So what we have done here is sort of a visualization of the clusters after, right, the end of the algorithm. Now like I said, this is done for a toy data set, but is still somewhat instructive, and I encourage you to sort of do it with other data sets as well. Okay. I hope you found this example instructive. The next example of an analytically solvable problem, right, that I want to discuss is that of principal component analysis in again in 2 dimensions. More than 2 dimensions solving analytically is not possible. So this is again principal component analysis in 2 dimensions. I mean, although you do not really need to reduce dimensions if you have only 2, right, that is very small number of dimensions, but again as a toy problem, as something that is instructive, it is quite useful. So here you are given the data matrix. So the data matrix X is as follows. So X is, so again there are 4 points here just to make it easy for us: 4 1 2 3 5 4 and 1 0, right. So that is the data matrix, and if you remember how we go about principal component analysis is, first we make the mean of each feature as 0, and of course we also make the standard deviation to 1, although I will omit that part here for simplicity, the second part. Now to make the mean of each feature 0, first you have to figure out what the means are. So you know that each column here corresponds to one feature. So the columns are features, that is always standard the way we have been doing it, and rows are data points. So if you want to find the average of the first feature, right, or the mean of feature 1, that is just, so there are 4 points, 1/4 of the sum of all the data points feature 1. So that is 4 plus 2 plus 5 plus 1. So that is 12 divided by 4, so that is 3, and then if you computed the mean of feature 2, that is again 1/4 of 1 plus 3 plus 4 plus 0, that is 8 divided by 4, and that is equal to 2. Okay. So this is where we are. So now if we zero out the means, so upon zeroing the means, right, you will get a modified data matrix. So I will denote it as X 0 feature mean. Okay. So if you subtract out the means of the features, so you have to subtract out 3 from everywhere in the first column, and you have to subtract 2 from everywhere in the second column. So if you subtract 3 from everywhere in the first column, so that will be 1 minus 1 2 and minus 2, 1 minus 1 and 2 and minus 2. and if you subtract 1 from every column on the right, the second column, so you have to subtract 2, sorry. So it will be 1 minus 2 is minus 1, 3 minus 2 is 1, 4 minus 2 is 2, and 0 minus 2 is minus 2. So the entries in the second column are minus 1, 1, 2 and minus 2. Okay. Now for simplicity, like I said, I am going to omit the part wherein we make the variances as 0, because that will introduce some other mathematical factors, but typically that is recommended. So instead what I will do is I will just compute the covariance matrix, right. So covariance of x you know is 1 over n minus 1 x transpose x, and here n is 4, right. There are 4 data points, so essentially n minus 1 is 3. So you have to divide everything by 3, although again for simplicity, mathematical convenience, I will not do it. The directions of the eigenvectors will not change, but typically it is recommended that you work with the covariance matrix. So because of mathematical simplicity, I will directly compute x transpose x and then look at the eigenvalues and eigenvectors of x transpose x. So now what is x transpose x? So this x transpose x, it refers to the data matrix with after standardization. And here we are going to, in this simple example, we are going to consider that as this X matrix. So X transpose is you interchange the rows and columns, so that becomes 1, minus 1, 2 and minus 2. The first column becomes the first row and the second column becomes the second row. So that is X transpose, and then you have X, which is again 1 minus 1, minus 1 1, 2 2 and minus 2 and minus 2. Okay. Now you know that when you multiply two matrices, then it is done row by column, right. So what you do is, and this most of you hopefully know, is you take the first row and then you multiply it by the first column and then you add up, right, whatever you get element wise, and then similarly you take the first row and the second column and so on and so forth. Okay. So if you did that here, so you will get 1 times 1 is 1, then minus 1 times minus 1 is also 1. So adding those two ones is 2, and then 2 times 2 is 4. So 2 plus 4 is 6, and then minus 2 times minus 2 is also 4. So 6 plus 4 is 10. Okay. So what you get here is a 10, and then I encourage you to look up or solve the other entries. So it will be 10, 6, 6 and 10. So as you can see, this is a symmetric matrix. Okay. So now to find the principal components, we need to find the eigenvectors. The eigenvectors and the eigenvalues. So together it is basically the eigenvalue decomposition. Okay. So how do we find the eigenvalues and eigenvectors? You know that if you have a matrix A and you want to find the eigenvalues and eigenvectors, essentially what you do is you write it as AV equals lambda IV. So you introduce the identity matrix of the appropriate size, and then bringing this to the left hand side is, and taking the V out, it becomes A minus lambda IV equal to 0, right. And when you want to find eigenvectors, right, you want this V to be a non-trivial vector. So the eigenvector is a non-trivial vector, meaning the vector V cannot be all zeros. Obviously if V was all zeros, you would get 0 on the right hand side, but you want a non-trivial solution, right. Those are the ones that are useful because they tell you, right, in which directions you will simply be stretching the vector if you operated the matrix A, right. This is a linear operation A times V, and then this is simply a stretching operation. So along which directions is multiplying by matrix A is simply equal to a stretching of the vector. So those non-trivial vectors we desire, not the 0 vector. So if this equation here has to have a solution, right, when V is non-trivial, right, the only way is for the determinant of the adjoining matrix A minus lambda I equals 0, right, and this is called the characteristic equation of the matrix. Okay. So now we have to write the determinant of A minus lambda I, and that needs to be set to 0. So essentially we have determinant of A, so A is 10 6 6 10 minus lambda, and the identity matrix of the appropriate size is 1 0 0 1, that is equal to 0, alright. And then this becomes fairly straightforward. So that is 10 minus lambda 6 6 and 10 minus lambda. The determinant of this 2 by 2 matrix is 0, and determining the determinant of a 2 by 2 matrix is really easy. You just multiply the opposite elements, right, and then subtract the result. So this becomes 10 minus lambda whole squared minus 6 squared, right, in this simple case, right. So that is lambda squared minus 20 lambda plus 100 minus 36 equals 0, and 100 minus 36 is 64. So this is the equation, and then this can be factored as lambda minus 16 times lambda minus 4 equals 0. So that there are two roots, lambda equals 16 or lambda equals 4. Okay. So these are the eigenvalues, and you can plug them back in the original equation AV equal to lambda V to get the eigenvectors. Okay. So if you go back to the original equation AV equals lambda V, right, let us do that. So A is in this case x transpose x, so that is 10 6 6 10, and then let us assume V as V1 V2, and then this should be equal to 16 times V1 V2. Alright. So that is where we are, and then this becomes a really easy system to solve. Again you have to do matrix vector multiplication this time. So that is this matrix multiplied by this vector. Remember we are doing everything analytically, but on a computer it will all happen numerically. So you have to have numerical algorithms of finding eigenvalues and eigenvectors, which of course we do not have the time to go through, but for those of you who are interested, I encourage you to read up about that. So if you multiply the matrix by the vector, you will get 10 V1 plus 6 V2 as the first entry, and 6 V1 plus 10 V2 as the second entry, and both of these together should be equal to 16 V1 16 V2, right. Now we can bring everything onto the left hand side. So we will have minus 6 V1 plus 6 V2, and here we will have 6 V1 minus 6 V2 equals 0 0, right. And if you divide throughout by 6, so essentially we have V2 minus V1 and V1 minus V2, they are both equal to 0 and 0, and both of these equations, the first equation the top, that gives you V1 equals V2, and this equation as well tells you that V1 equals V2. So now this is obvious that you only get you are not able to fully specify it, because as discussed, I mean vector can be scaled by any number and it will still remain the same vector. So you only have to find it up to a constant. So therefore the V vector is V1 V2, and here we know that for this eigenvector V2 is equal to V1, so that is just V1 times 1 comma 1. Right, this particular vector, and since the constant does not really matter, you can say that the first principal component, or at this point you can't say, so one of the principal components, so one of the PCs is 1 comma 1, alright. So, I hope this makes sense. Now, all that remains is to find out the second principal component, and you can do it in a similar way, right. At this point, yeah, we had two eigenvalues and we used the larger eigenvalue to determine the eigenvector. So, this is actually indeed the first principal component. So, this is indeed the first principal component. Since we have used the larger eigenvalue as it corresponds to the largest eigenvalue. Okay. Now, how do we visualize this? Just like we did it in the previous problem, let us try to visualize it, right. It does take some time and effort, but it does give you some useful insights, right. So, that is those are the two features, let us call them x1, x2 in this case, and what are the points? The points that we considered in the problem, these were 4, 1. So, x1 was 4 and y1 was 1. So, let us say that is somewhere here. Then you had 2, 3, right. So, where is 2, 3? So, 2, 3 will be somewhere here. So, if we mark it, probably it is easier. So, let us this 1, 2, 3, 4, 5, and then on the y axis we had 1, 2, 3, 4, 5, and we may also need -1 here and -1 and -2 here. So, like I said, the first point was 4, 1. So, that is what we have plotted here. Then the second point is 2, 3. So, that is here. The third point is 5, 4. So, that is here, and the last point is 1, 0, right. So, 1, 0 is somewhere here. Okay. So, this was the original data matrix, and after that we did transform the data, right. So, when you transformed the data, it became the transformed data, let us see where it is, was, and I will try to use just the black color for that. So, this if we put it everything in blue, this is the original data, and then if you put everything in black, that is the transformed data. So, the transformed data was 1, -1. So, that is here. I will put a circle around it just to distinguish it. Then there was -1, 1. So, that is here, and then there was 2, 2, that is here, and then -2 and -2. So, that is somewhere here. Okay. So, the original data is shown in blue here, and this is essentially the transformed data. After zeroing the means. Okay. And the first principal component is 1, 1. So, that is the vector which has equal length in the x and y directions, and that is basically this direction, right. So, this is the first principal component, and you can see that it is indeed the direction in which the data has the maximum variance, right. So, that is the direction along which the data varies the most, and therefore, it is the first principal component. Okay. So, I hope this example right again gives you some physical insight into what happens in a computer. Of course, the computer does everything numerically, whereas we are trying to do it analytically to get some physical insight. So, with that I will end today's lecture with some hopefully illustrative examples. I hope you enjoyed the content here. Thank you for joining today, and I look forward to seeing you next time.